Optics and Optoelectronics from University of Calcutta, India in 1995, 1998 and 2000 respectively. He completed PhD in Computer Science and Engineering from Jadavpur University, India in 2008. He is the recipient of the University Gold Medal from the University of Calcutta for his Masters. He is the recipient of the coveted National Award Adarsh Vidya Saraswati Rashtriya Puraskar for Excellence in Education and Research in 2016. He is the recipient of the coveted Bharatiya Shiksha Ratan Award conferred by Economic Growth Foundation, New Delhi in 2017. He received the Honorary Decorate Award (LITD) from the University of South America and the Southeast Asian Regional Computing Confederation International Digital Award ICT Educator of the Year in 2017. He has been appointed as the ACM Distinguished Speaker for the tenure 2018 to 2020. He received the Young Scientist Science and Technology Award from CSERE India in 2018. He is currently the principal of RCC Institute of Information Technology, Kolkata, India. He is the member of Editorial Board of Applied Soft Computing Elsewhere EV and serving as the series editor of the IGI Global Book Series Advances in Information Technology, Quality and Management from January 1, 2017. There are no words which can convey awe and respect for you, sir. I welcome you to come on the stage.
First of all, I'd like to thank the organizers for inviting me over here. No, I think that taking a lecture in the international conference, especially from an Indian researcher, it will seem boring. Okay. But then I have to do my duty. You have to carry forward, provided that you remain as calm and quiet as possible, because it may happen that in the middle of the lecture, the entire room may be found empty. Anyway, let us hope that we will remain as long as the lecture is on, but I will take very few time of you. In fact, within half an hour I will like to cover up the entire topic. You see, just the topic itself is about something which is relevant in present scenario. It is about something which is referred to as clustering or classification. Now, I will start with a simple example over here. You see, from this microphone example itself, okay, the first microphone was not working properly, but it is working fine. You see, there are two clusters. These are two clusters of microphones. One microphone working properly, another one not working. So this is all about clustering. That means you divide number of elements into different groups depending on their characteristics. This is all about clustering. So moving ahead, we are going to discuss about something which is very prominent nowadays. What is that? It is something related to clustering, but then you know that in any clustering example or any clustering application, you have to know beforehand what are the number of clusters. For example, in this microphone example, you see there are two clusters, isn't it? One is a good microphone, another is a bad one. So you know beforehand there are two clusters possible over here. But think of the situation where you do not know how many clusters are there beforehand. That is the challenge. So given that situation, is it possible to find out the optimal number of clusters? That is, optimum number of clusters that can faithfully classify the data set or the number of elements. This is all about automatic clustering. And then the objective is to enhance the performance of this clustering procedure by taking the help of quantum computing, a very recent topic which has come into existence, quantum computers. So we touch a little bit of everything as we move on. You see, already told before, this clustering is a way of putting together data samples based on some features, similarity or dissimilarity of features. It is a form of unsupervised. Why unsupervised? Because you do not know beforehand what you are going to do. That means there is no way to learn beforehand, to know beforehand what is going to happen after the clustering test. That is unsupervised. Okay, it is a part of machine learning. And then obviously it is a method of data exploration. You explore the data set, you explore the number of elements in a set, and then pick and choose the features, relevant features, and then group together in 2 or 3 or 4 or n number of clusters. That is the essence of this topic. Here is an example, small example is here. You see, this red circle indicates a cluster. Similarly, the other two clusters are there, represented by oval-shaped circles. Why? That means there are 3 clusters over here. So how do you determine how many clusters are there? Just by grouping together different points represented by crosses over here. So here you see, obviously you see in the red circle, all the cross points are very near to each other. So you group them together. Similarly, the other 2 ones at the top post, they are similar to each other in the same, they are near to each other. So you group them in the another cluster. Again, you go for the other 3 remaining data points, and then depending on their similarity as regards to the distance between them, you group them in a different cluster. So you see, you can use the clustering algorithm to classify the data points, the clustered data points into a number of clusters depending on some feature. There the feature is the distance. Okay. So these are some mathematics over here. You see, if a data set is there containing elements x1 to xn, it is any number of elements are there. And suppose you are dividing the data set into p number of clusters. The clusters are represented by some cluster centroid, cluster center. Okay, each and every cluster you determine comprises the center or centroid. Let us represent it by C. So, since there are p number of clusters, obviously, how many cluster centers will be there? C1 to Cp. Okay. And there are some features of the clustering algorithm. For example, no two clusters will overlap. That is first and foremost condition. No two clusters will overlap. That is one thing. And moreover, just going across the mathematics, you will see that first of all there will be no overlapping, and next there will be some distinctness in the cluster. Each and every element you cluster together will be distinct as regards to the features used for clustering. Okay. Now what is a good clustering? Good clustering means, you see, since we are grouping objects depending on features, always targeting objective is to group them based on the similarity between the features of the different data sets, the data points. That means those data points which have similar features will be grouped in a single cluster, and those who have dissimilar features will be grouped in another cluster. But then, within a single cluster, the intra-class similarity will be high. It means if you put several data points within a cluster, all the data points will be similar to each other very strongly as regards to the feature selected. Okay. Similarly, since you have more than one number of clusters, each and every cluster will be different from the others as regards to the inter-cluster similarity. What is inter-cluster similarity? That means within a cluster, the similarity is referred to intra-cluster similarity. And between two or more clusters, that is referred to the inter-class similarity. That means the inter-class similarity will also have to be very high. Okay. Oh, sorry, no. So you see, these are the conditions for having a good clustering algorithm. And obviously, after clustering, in order to judge the quality of the clustering, you have to measure its quality, evaluate its quality. So how to do that? You see, before going forward, just told before that in a clustering algorithm, no two clusters will overlap. This particular aspect is generally envisioned in what is referred to as hard clustering. Hard clustering means that no two clusters can overlap. But there is another version nowadays which is referred to as soft clustering, where there is a possibility that one single element belonging to one cluster may also belong to another cluster. That is, there may be overlap. For example, you can always see, you can put a pair of sneakers means shoes, okay, into two clusters simultaneously. One is sports apparel, another is shoes. So you see, a pair of sneakers can be classified or clustered into more than one cluster. One cluster being the sports apparel, another cluster being the shoe. In both the cases, its containment is true. That means you can always say that a pair of sneakers is both a sports apparel as well as a type of shoe. So you see, a particular element can belong in more than one cluster. That is soft clustering. Okay. And in some examples over here, how clustering can be used in several domains of engineering and science, starting from land use, information retrieval, then climate understanding, all these things, demographic changes, all these things, and then also nowadays in biomedical imaging. So different scores of applications are there, but it's good to use. Clustering is very good, it's a good application which can be used for retrieval of necessary or relevant information from a data set. It can be used in different cases. Now, before going for a clustering, the conditions you must have. First is the partitioning criteria. How you are partitioning different elements? What is the basis of that? That is one partitioning criteria. It may be either single level or hierarchical. Hierarchical means to start with a number of clusters and then you will define it and then get down to a more defined number of clusters. That means the number of clusters at the final stage will be different from the initial one. That is the hierarchical cluster. And then separation of cluster already told, inter-class and inter-class similarity. And then obviously similarity, how to measure the similarity. You may go for distance based, Euclidean distance or connectivity based, it is distance density. And then obviously you may either use the full data set for clustering or you can use subspaces of the data set for clustering. Practice is similar to the hierarchical clustering. You start with the entire space, do some clustering, find out some clusters, define them, then get different number of clusters, which are more defined. These are different major clustering approaches: partitioning approach, hierarchical approach, density-based approach, or deep-based approach. These are not the few details. You see, given some idea about clustering, what is the clustering, what is the objective, how to do that, what are different procedures. Now, what is quantum computing? The quantum computing, you see, the basic of quantum computing is similar to the conventional computer. The sense it is also a computing paradigm. But again, the difference is, in a quantum computer, that is conventional computer, we have bits to store information, bits, 1 to 0. But in the case of quantum computer, you do not have 1 and 0. You have qubits or quantum bits. That those are nothing but this is a phase information. Phase information, which are combination of 0 and 1. It means in conventional computer you have only zeros and ones to represent information. But here you have zeros, ones, and combination of zeros and ones. This combination is referred to as superposition. Okay. So these zeros and ones are little bit different from the zeros and ones in conventional computer. So these zeros and ones are referred to as qubits. Either you have a 0 qubit, collection of values in the form of a superposition of zeros and ones. Okay. Now, what actually happens over here? You see that is you have a multiple number of solutions for a single problem, for a single variable. So how do you get the actual variable? So this actual variable is obtained whenever you go for some another operation of this particular qubit, resulting in either 0 or 1, depending on the probability. Okay. So these are some complex procedures, but for the basic understanding, these are either 0 and 1 or a combination of 0 and 1. Another thing you see, any particular qubit in the form of alpha beta or 0s and 1 combination of 0s and 1s can be manipulated by rotation gate. This particular gate is referred to as rotation gate. By a particular qubit alpha 1, beta 1 can be operated upon by a matrix operation to result in another qubit. So that is the basic object. You see, this type of operations are not available in the conventional computer. But inspired by the principles of quantum mechanics, you can do some primary operations on these particular qubits to generate different qubits. Okay. So these are the features, the very useful features of quantum superposition. I already told you, different qubits, either zeros and ones, can be manifested in the form of either zeros and ones or a combination of zeros and ones. The combination is the first one. Okay. And another one is interference. What is interference? You see, now I already told you, because these zeros and ones are not actually two bits. These are actually phase information. These are actually wave functions. Okay. So if two wave functions are in phase with each other, they cohere together to form another wave function. This phenomenon is referred to as interference. And in fact, this idea has been borrowed from quantum optics. Okay. So here you see two different wave functions. One represented by a combination of zeros and ones, another by another combination of zeros and ones. If they are in phase, they are referred to as coherent wave functions. And they can cohere together, interfere together to form another wave function of different combination of zeros and ones. Okay, this is interference. And that means you are starting with some values. You are operating them together by use of using interference function, and then resulting in another wave function. Now, to get back the original wave function out of the resulting out of the interference, what to do? You can do the reverse procedure. That is, destroy the interference. Destroy the interference. How to destroy? That is referred to as measurement. When you measure a particular qubit, it either boils down to 0 or 1, depending on a probability. So that means the interfered qubit, if you measure it, say, it will either boil down to one single qubit having the state 0 or another qubit with state 1. That means it is now similar to a conventional computer. In a conventional computer, you only have zeros or ones. But here you start with a combination of zeros and ones, interfere and do some operations to get something, and the final result, when you measure the final result, you get back again either 0 or 1. Okay? Another property is entanglement. It is a very useful property. Nowadays used in teleportation. That means transmission of information from one point to another point. This entanglement has come up. Research is going on. So you see, this entanglement indicates a correlation between the different states. Correlation in the sense, if two qubits are entangled, that's the property of entanglement. Okay, if they are entangled with each other, that means that if you measure one qubit, if it results in a value 0, the other qubit will automatically yield 1, and vice versa. Okay. So it's very important. You see, if you want to transmit some information by encrypting it, if you take the information as well as the encryption, it's the key as both quantum version or the quantum keys. So one to measure it at the other end. If those two, the ciphertext and the plain text are entangled with each other, at the other end, if you measure it, if you get the ciphertext, automatically get back the plain text. Since they are entangled with each other. The properties which nowadays used, however, extensive research is going on because these things have not been realized in practice yet. Now, again come back to clustering. Already told you what is clustering, how it is done, what is the objective, what is the application, what are the different approaches, and then what are good clusters. So, given an algorithm which can cluster, you have to validate whether the clustering is very good or not. Okay. And whether the clustering algorithm is generating or producing valid clusters. Okay. The clustering, actually, you see, the basic principle is that in a clustering algorithm, if you have n number of points, number of clusters must be greater than 2. You cannot have a cluster with value 2. That is, two clusters, these are the trivial case. Having two clusters in a data set. So, good algorithm generally produces clusters greater than 2. Number of clusters greater than 2 and less than obviously n. Because it is not possible that all the n number of data points are individual clusters. It is not possible. So, a number of clusters must be greater than 2 and less than n. So, you have to validate it by using some validation techniques. You see some examples over here. Sir, the left-post figure indicates clusters in random technique. Random distributed. Right now you see clusters already introduced in using the T-scan algorithm. In K-means algorithm is another clustering algorithm. We put another set of clusters and completing with another procedure. You see that different clustering algorithms produces different results. That is why one clustering algorithm is efficient than the other and is applicable in a particular application domain. I will not go by these very detailed things over here. Just come to the point actually. How to measure the clustering? How to measure the clustering? There are different indices. One is external index, internal index, and index. External index means used to measure the extent a cluster level matches sub-type cluster. That means it is a supervised case. The supervised case means you have a set of data points, n number of data points, okay? And out of which some subset of the data points are labeled, already labeled. You know before that which particular data point belongs to which cluster. So the information is there. Prior information is there. Based on the information, you cluster the remaining data set and then match it with the already defined labels. External index, okay? And you see how much it matches with the already supplied labels. This is is external index, and internal index is that which without respect to any external information is the answer of respect. And relative index is measuring cluster validity in 2 or more clusters. Different standard indices are there. One is DAR index, population, one here. The index aims at identifying sets of clusters that are compact and well. That means something which relates to both inter-cluster similarity and inter-cluster similarity. Another challenge is continuing, and now you see the important thing is that large value of DAR index corresponds to good clusters. If you compute, first of all you take a data set, you cluster it before using an algorithm, and then you compute the DAR index. The value of the DAR index comes up to very large. That means it is a good cluster. Clustering algorithm is performing well. And then DB index, David Coleman index. Here, if you see minimum the value of DB, the better is the clustering. It is equal. Okay. And then another is zero coefficient. And the closer is the value of the coefficient to 1, the better is the cluster. And then I index. I index is another type of clustering index, or cluster validity index, where you can determine whether a cluster is valid or not, depending on this particular mathematics. In fact, I am not going to detail the mathematics. Something which relates or rather takes into account both the inter-cluster similarity and inter-clusters in different forms. Okay. Now, I think the objective was to find out the optimum or the automatic cluster. You do not know the number of clusters that would have used in a given cassette. You try your algorithm, it automatically finds out the clustering, the number of clusters and cluster. How? This is actually a sort of optimization technique. Okay. So different optimization techniques are in vogue. The first one is particle form optimization. I think most of you are aware of this. Not skipping this. Then you have differential evolution, another type of algorithm. And then simulated analysis. Then you have different algorithms. Starting from genetic algorithm, different algorithms coming up. Nowadays, more at first, nature discrete algorithms are coming up. Huge work is going on. Like some examples of the DATSAT algorithm, cloud correlation algorithm, span mobility algorithm, kidney algorithm. So the different algorithms are coming up. Okay. So there is no end to this. Anyway, we are just working upon only standard algorithms which have been used, widely used over the years. But this is simultaneously which is inspired by the annealing process in mechanical engineering. Now see, each and every optimization algorithm starts with a chromosome. Chromosome or a set of possible solutions. Okay, you optimize it. You start a set of possible solutions. You compute the fitness of each and every individual chromosome, find out the best fit chromosome. Then iterate, come out with different operations like several standard operations like crossover, elimination are there, which modifies that chromosome, modifies solutions, and then you come up again, go to the next iteration. Pick out the best chromosome till now, and then you generally go for a specific number of iterations, and then you come out with a optimized solution, which indicates the best possible solution out of the entire set of solutions, initial entire set of solutions to start with. What is the nature of the structure of the solution? Because structure may be represented by this. And you see, in the case of conventional genetic algorithm or simultaneity or any algorithm, any evolution algorithm, you start with a chromosome. It's a collection of bits, zeros and ones. If you go for binary version, okay, zeros and ones. Now the objective is to devise quantum version of those algorithms and apply it to automatic cluster. So what? If you go for quantum version, obviously there are no zeros and ones, there will be qubits. So the entire chromosome string comes up like this. You see, alpha 1, beta 1, alpha 2, beta 2, alpha 3, beta 3, this alpha, P, beta. That is P number of bits. So you see, each and every one is a chromosome by is a gene by itself. Phi 1, the wave function, phi 2 is the wave function, phi 3 is the wave function. So these are qubits. So your representation string previously was in the form of zeros and ones, but here it is in the form of collection of qubits. Because you are switching to quantum machine. And these are some algorithms which have developed over the years. And this is, you see, this is a quantum impact particle form. You are converting the particle form of information, this conventional particle form of information, PSO, into a quantum version. So this is the algorithm over here. It's simple. You start with the string representation, you do some manipulation, quantum manipulation over the interference, all these things over here, you generate the trial solutions. Then you compute the fitness, go for crossover, you do same thing. Same thing is going on here, but in the quantum domain. So in the case of crossover, you have to use quantum crossover. In the case of mutation, you have to use quantum mutation. And finally, obviously you see, most of all over here, maybe wondering, what is quantum? Because quantum something which is different from the conventional quantum computing. So after all, whatever you do in the quantum domain, when you want to get back the result, you have to have the conventional domain again. That means you have to measure the quantum system and then find out some result which is either zeros or ones. That means you come back to the conventional domain again. You start with the conventional system data set, you convert it to quantum intermediate, do some operations or rather run the algorithm, and then after getting the result, optimized result in the quantum domain, you do some measurement, quantum measurement, to convert the quantum system back to the conventional system. Okay. Now these algorithms, what these algorithms are doing, these algorithms are actually using the both indices, clusterability indices, DB index, DAR index, I index. That means, first of all, what is the actual, I am not going into details of algorithm. You see, it starts with the data set. You are generating some trial solutions in the quantum domain, chromosomes. Okay. Then it is finding out that is these chromosomes, each and every individual chromosome represents some clusters. Okay. Some possible clusters. Possible clusters, possible random clusters. You take each and every individual cluster, compute the DAR index or the DB index or I index to see whether it is coming good or not. Then you pick that good ones, then you go for crossover, quantum mutation. Then again you generate new morphings, go to the next generation, in this way you go on optimizing. Finally, after certain number of iterations, you calm down or boil down to an optimized solution. The optimized solution represents the string chromosome, which represents the optimum clusters, which have been validated by the different indices, either DAR index or DB index or I index. So it is a optimization problem. Another algorithm is here. Very simple algorithm, similar algorithms. It is a quantum version of the differential evolution and quantum version of the simultaneity. Now see, always, now you is a researcher, so what you actually do, you do research for fun. Okay, not for our earning, you do research for fun. So obviously you want to see, whenever you develop an algorithm, you want to see whether it is working fine. Okay. So I'll give you some examples of experimental findings. We have applied it to some benchmark data sets in the form of images. We have demonstrated first of the quality solution using we can use DB index, accuracy. We have also used some statistical tests to get the superiority of the algorithm, standard error, compression. These are the different measures, different criteria which the algorithm is actually evaluated. This you see these 4 images. We have applied the algorithms on these 4 images. We have applied the quantum version of QIACPSO. What does the entire thing means? Acronym means. QI means quantum is bad, AC means automatic clustering, PSO means particle from operation. Similarly, QI, AC, DE, quantum is bad, automatic clustering, differential evolution. Okay. We apply these 2 algorithms on these 4 images over here with the different parameters listed below. And these are the simulation results. Obviously, we will not be interested in these results. But if you find out, you go to this 2 tables, table 5. Table 5 is indicate the comparison of the different algorithms, and it is found that QICPSO PSO. The PSO is working better than the ICICC. Now what is this? You see, if you go back, you see, sorry. You see, these are the number of optimum number of clusters 7, 10, 7, 9, 8 for different generations. We are getting the QAC PSO algorithm for the Oman image. We are getting these values, and this is the fitness function. That is the index. For the big image, the NC is the optimum number of clusters 6, 5, 6, 5, different generation, different run of value. Okay. And then you are taking the average. Average is the number of clusters of the different definitions and different runs, and then you are taking the final result. These are the statistical indicators that indicate that the PSO algorithm is performing better than the GL. So we have again applied the simulated version, simulated algorithm over these images. So all real life images, and then we are taking some guesses and you have to see for the couple image, the limit is cut off to 0.036 and T is the time of function time, 6 milliseconds. And NC is the 4 number of clusters which have come up to number of clusters 4. Again, in the couple image, there are 4 clusters. Automatically it determines how many clusters put there. 4 clusters are there. So this is the beauty of the algorithm. You do not need to provide any information regarding the number of clusters before that, which is generally done in conventional clustering algorithms. Here you only give the data set, the algorithm itself finds out the optimum number of clusters which will give the best clustering result. Now here also you see some statistical tests have been performed, but it again indicates it is part of this algorithm is performing best in the case of couple image, significance level is 1, in the cloud it is not so good, in the clear image it is 1, in this image 1, 1, 1. So it is not performing well in as far as image 2 is concerned. So now the question may arise, why are you using quantum? Okay, so we have not put the results over here. In fact, these algorithms which are developed have been compared with the classical versions of the algorithm, with the same thing. Just we found that these algorithms are more time efficient than the existing algorithms in orders of tens of seconds. So you see, if for instance the increase in time complexity is tenfold, you can do it faster. Obviously, what are the application areas? I already told you. One of the key application areas of these particular techniques, clustering techniques, is in the defense. For example, in the border, you may try to segregate rather cluster different tags, enemy tags. Okay. So these algorithms are generally used over there. So if you do it faster, it will come in good state. It will be used for real-time applications. So that is why we have resorted to quantum-inspired domains to get faster results. These are the list of references, a subset, any query.
Thank you so much, sir, for your valuable information. I ask from audience if you want to ask anything from sir.
Any question from the audience side?